So in this video we will go over the basics of least squares adjustments. And least squares adjustments are used when there are more equations than unknowns. If we have more equations than there are unknowns to solve a system, it means that it's an overdetermined system. A unique solution is a solution where there are as many equations as there are unknowns. So let's take two equations, say a plus b equals 1 and a minus b equals 0. No matter how this is solved, the solution is always going to be the same. So I can add these two equations together. A plus a is 2a, b minus b is 0, 1 plus 0 is 1, a equals 1/2, substitute it back and we get b equals 1/2. Or we can subtract the two equations from each other. So a minus a is 0, b minus a minus b is 2b, and 1 minus 0 is still 1, so b equals 1/2, substitute it back, and we get a equals 1/2. Or we can solve, or we can rearrange the variables in one equation. From this we can bring b to the other side, so a equals b, substitute that back in here. We get b plus b equals 1, 2b equals 1, so b equals 1/2. Since a equals b, we get a equals 1/2. So no matter how it's solved, the solution is going to be the same. However, if we add a third equation, let's say that third equation is going to be an identity. Say a equals 0.6. Now we have three equations with two unknowns. It's an overdetermined system. And there's no one perfect way to solve this. So if a equals 0.6, if we substitute that back into the first equation, we get b equals 0.4. Substitute a equals 0.6 into the second equation, then b equals 0.6. So which one of these is correct? Well, neither is correct. There's no one perfect solution to this. And this is why least squares was developed, in order to solve situations like this. And why is it called least squares? Because this solution minimizes because this solution minimizes, or least squares minimizes, the sums of the squares of the residuals. Now notice that I didn't write error, because we don't know the error, and error is only with respect to an errorless value. A residual is the difference between the measured and the adjusted. Residual is the difference between measured and adjusted. So the least square solution minimizes the sums of the squares of the residuals. That is, generically, if we represent V as a residual, then the residual of the first equation, in this case squared, plus the residual of the second equation squared, plus the residual of the third equation, sum them all up, and that will be minimized. So the question is, why are we minimizing basically a quadratic? We could also minimize the sums of the absolute values. That is the absolute value of the first residual plus the absolute value of the second residual plus the absolute value of the third residual could also be minimized. And that's another method. That's another way to go. However, there are some drawbacks of that. And what would be a drawback? Well, let's take a look at the how an absolute value function looks like. It looks something like this. And over here, y is equal to the absolute value of x. And I mean, this looks okay, but there's a break right there. At the minimum point. And if we take the first derivative of this, so y naught, let's take y naught. It's going to be basically -1 up to the y-axis, and then 1 after or to the right of the y-axis. And what's the value right? What's the first derivative value right at the y-axis? Well, it's undetermined. And a very basic way to find the minimum value of a function is to take the first derivative and set it equal to 0. But right at the minimum value right there, the first derivative is undefined or undetermined. It could be 0, it could be 1, it could be -1. It's just undetermined. And let's take a look at how the quadratic function looks like. Say y equals x squared. It looks something similar to this. It's a nice smooth function. There are no breaks like in the absolute value function. And let's take a look at the first derivative. The first derivative of this is defined everywhere. And it's going to be equal to 2x. That is, once again, it's a nice smooth function. It's defined everywhere. And it's very easy to find the minimum value, set the first derivative equal to 0, and then solve that. So the reason behind the least squares is the reason behind we're using a quadratic function is that the function itself is a smooth function. It's defined everywhere. Its first derivative is a smooth function, and it's also defined everywhere. So let's take a look at how, if we use how we can set up an equation system in matrix form. Let's take a look at the first two equations out of these three. So if we take a look at the first two equations, how could we set those up in matrix form? And any system of equations can be set up in matrix form in the following way, where y equals a times x, where y is the vector of the knowns. A is equal to the partial derivative, well, not the partial, but the Jacobian with respect to the unknowns, and x is our vector of the unknowns. So if we look at the first two, our vector of the knowns is just going to be equal to 1 and 0. Our Jacobian is going to be the partial derivatives with respect to the unknowns. And it's going to be a 2 by 2 matrix. First part partial with respect to A and partial with respect to B. The partial with respect to A in the first equation is 1. Partial with respect to B is also 1. For the second one, it's 1 and minus 1. And our vector of the unknowns is simply just going to be A and B. And it has to be in the same order as the Jacobian. It doesn't matter what the order is as long as the order is consistent. I can put B as our first derivative, but then B would be the first unknown in the x vector. So how would we solve this to find x? If y equals ax, then we can multiply with A inverse from the left side. So A inverse times y equals A inverse times A times x. And A inverse times A is just an identity matrix. So if we have a unique solution, the solution is going to be A inverse times y. So let's see if that actually works. The inverse of A is going to be zero point 0.5, 0.5, 0.5, and minus 0.5. And then A inverse times y is going to be equal to 0.5 and 0.5. So we got the same solution as solving it algebraically. We got the same solution with a matrix setup as we did with algebraically. However, what happens if we have a third equation? We can still set it up this way. 1, 0, and 0.6 is going to be our third value. Our unknowns are still A, B, and our Jacobian is going to be 1 and then 0. Add a third row. What happens to a matrix when it's not a square matrix? It can't be inverted. So we have to find a different solution than A inverse y. And this is the idea, and this is how the least squares solution was developed. We add a residual to each of these equations. So let's take a look at this time for each equation. So we have a residual in this one, we have a residual in this one, and we have a residual in this one. So then our equation system becomes v plus y equals a times x. Or basically v is going to be equal to a times x minus y. And our stipulation is that the sums of the squares of the residuals are going to be minimized. And we can represent the sums of the squares of the residuals in vector form as v transpose times v. And that's going to be basically the sums of the squares of the residuals. So v transpose v is equal to the sums of the squares of the residuals. And we want to minimize that. So in order to minimize it, let's take the partial derivative. So the partial derivative of v transpose times v is equal to 2 times v transpose dv and we want to minimize that. That is, we set that equal to 0. So the partial derivative of this with respect to v with respect to x, that is, we take dv with respect to dx, and that's just going to be equal to a. And we can rearrange that to have dv equals a times dx. Since dv is equal to a times dx, we can substitute that back into this equation. So we get 2v transpose a times dx that is, we substitute this back into here, and that should equal to 0. That should be equal to 0. And so we can divide that by 2. And a matrix identity is that Vt times A is the same as A transpose times V. So from this we can get if V transpose A is equal to A transpose V, and we can set those equal to 0 from this, since dx is never going to be equal to 0. So then let's substitute these back. And multiply. So let's put this back into our original equation. And we get A transpose times A times X minus A transpose times Y is equal to 0. And this is what's going to be called our normal equation. And we can also represent this A transpose A is big N. That's the normal matrix. And A transpose Y is the little n. That's the normal vector. So from that we get that n times x minus n is equal to 0. Or the solution is x equal n inverse times little n. Or A transpose A inverse times A transpose times Y is going to be our solution to our unknown quantities, or the adjusted unknown quantities. So this is going to be the adjusted value. And it's not going to be a perfect fit, but this x-adjusted value is going to minimize the sums of the squares of the residuals. So let's take a look at how that would look, how the solution would look like for our three equations over here. So our A matrix is going to be the partial with respect to the unknowns, the partial with respect to A, and partial with respect to B. So it's 1, 1, 1 minus 1, and 1 and 0. There's no 0 in the third, or there's no B in the third equation. Our vector of the knowns, 1, 0, 0.6. And our unknown quantities, vector of the unknowns, is just going to be A and B. And our solution to the adjusted is going to be equal to A transpose A inverse A transpose Y. And A transpose A is now going to be a square matrix, so we can take the inverse of that. So A transpose A is going to, our normal matrix, is going to be equal to 2, 0, 0, 2. The inverse of that is going to be 0.5. Zero, zero, and 0.5. A transpose Y is going to be equal to 1 and 1. Oh, that's not right. So then A transpose A is going to be equal so A transpose times A is going to be equal, it's going to be a square matrix, 3, 0, and 0, 2. So the inverse of A transpose A, or normal matrix, is going to be 1/3, 0, 0, 1/2. Our normal vector is going to be A transpose times Y. Is going to be 1.6 and 1. So x adjusted is going to be it should be n inverse times n. that's going to give us the solution of 0.5333 and 0.5. And it's going to be in this, and this is going to be the adjusted value of A and B. So how do we calculate the residuals? The residuals are calculated A times X adjusted minus Y. And that's going to give us a residuals of 0.0333, 0.0333, and minus 0.0667. And the residuals are small, that's what we're looking for. And the sums of the squares of the residuals, which is V transpose times V, should be even smaller. And that's going to be 0.0067. So it looks like we're on the right path. And least squares was specifically developed for surveying in the late 18th, early 19th century. And it's a byproduct of the Industrial Revolution. The Industrial Revolution allowed the mass production of goods. And before the Industrial Revolution, property had, or real estate had no monetary value, or it didn't really affect, or most people could not afford real estate. Only the king and the king's vassals could afford real estate. That's where the name real estate actually comes from. Real does not mean tangible. It's from the Spanish word real, or royal. That is, only the royals could afford real estate before the Industrial Revolution. And it didn't matter, so it didn't matter if somebody had real estate. It didn't really have all that much value. I mean, of course it had intrinsic value. It didn't really have monetary value. It had intrinsic value because, of course, that's where the crops were grown and people went to the forest to cut the wood. And the Industrial Revolution actually changed all that, because the Industrial Revolution allowed real estate values to fluctuate, the prices to fluctuate. If the real estate was closer to a mine or closer to a city, it probably may have had a higher value. If it wasn't, it may have had a lower value. So before the Industrial Revolution, there was no real need to survey a property. After the Industrial Revolution, when property values started to fluctuate, and taxes were based on property values, more and more people wanted their land surveyed in order to pay the minimum tax necessary. And more surveys obviously resulted in more and more surveying results, or surveying measurements. And more of these measurements were somewhat contradictory to each other, and their method was needed to be devised to adjust these surveying results. And that's where least squares comes in. It's usually attributed to Gauss. However, Laplace also developed a similar a similar method, and usually it's called Gaussian least squares or ordinary least squares. You can decide for yourself whether you want to believe it. Who developed it? Was it Gauss or Laplace? And the first actual use of the least squares method was in the Venus transit of 1790. That is when Venus crossed over the face of the sun. This was a good method to determine the distance from the Earth to the sun. So all these scientific societies send out surveyors to various parts of the world, because by that time, by 1793, the Industrial Revolution was in full swing. So more and more people could afford surveying instruments. Before the Industrial Revolution, the surveying instruments were made in one shop. That is, one shop created the telescope, the lenses, fitted the lenses and polished the lenses into the telescope or the barrel of the telescope. And the Industrial Revolution changed all that, where one company or one shop made the lenses, another shop made the barrel of the telescope, and another shop put all these together. So the Industrial Revolution resulted in the distribution of work. It also resulted in the mass production of goods. All this created lower and lower lower and lower prices. The pressure on the prices was to become lower and lower, since more and more shops were able to create similar products. So anyway, all these scientific societies finally had enough money to buy surveying instruments, telescopes. Up until the Industrial Revolution, once again, only the royal surveyor or the royal astronomer had enough money to buy these instruments. And so all these societies sent various surveyors to all over the world. And the idea was that if we have people surveying all over the world and they measure when first Venus touches the outside of the sun, and then transits across the sun, hits the other side of the sun, and by that time the radius of the Earth was fairly well known. So if they measure this angle in one place, measure to the same points from another place, and measure to the same points from several other places, we can actually determine or get a good idea of the distance between the center of the Earth to the outside of the sun. And that's basically one astronomical unit. And they got pretty close, because the difference between their measurements and current measurements is only about 5% off. And it took them years to do this adjustment, because obviously in 1790 there were no computers, so they had to do everything manually, collect the data, process the data, and if they made a mistake they had to start all over. They had hundreds of measurements, so their Jacobian matrix was a couple hundred rows and a couple hundred columns, and trying to invert that manually was a difficult task. So anyway, that's just the background of the least squares.